My name is Amanda Luby. I am a statistics professor at Swarthmore College outside of Philadelphia, and today I will be talking about psychometric analysis of forensic examiner behavior. This is a paper that was published last summer in Behavior Metrica, which is a quantitative psychology journal. And my co-authors on this paper are Brian Junker, who's a statistician at Carnegie Mellon, and Anjali Mazumdar, who is at the Alan Turing Institute in London. And so the paper that I'll be talking about today is available online, both at the CSAFE website, and I think I have the link right, and then it is also available open access from the journal itself. And so if you just Google the title of the paper, you should be able to find it pretty easily. And so before I get started, I think it's just really helpful to define what psychometrics is. And so psychometrics is really psychological measurement. And so this is statistical methods for analyzing survey data, tester exams, ratings, and things like that. So where people are kind of responding to questions or to items, and we want to kind of capture that variability. And so I'm primarily interested in measuring differences between individuals. And so within the context of forensic science, really the goal of this paper was to use behavioral models from psychometrics to better understand the operating characteristics of identification tests that fingerprint examiners perform. And so the data that I'll use throughout this talk today is the black box study from the FBI and Noblest that was done in 2011. And so the goal of that study was to estimate casework error rates in latent print comparisons. There were 169 participants that were practicing latent fingerprint examiners that were recruited for the study. There was a question pool of 744 items. Each item was a one-to-one comparison, and all of the items were known source. Each examiner saw roughly 100 questions. So every examiner did not see every item in this study because 744 comparison tasks would have been a lot. But participants were given several weeks to complete the exam, and the test conditions were not controlled. And so people could do the test either in their workplace or at home, or kind of do a few questions at a time, which is a little bit different than a lot of other psychometric applications. And so the main results from this black box study, which I assume a lot of you are familiar with, was to estimate the false positive rate, which is making an individualization when prints came from different sources. And so this type of error can lead to innocent suspects being prosecuted. And this was found to be very, very low. So 0.1% or 1/10 of 1%. And then the other type of error is a false negative rate. And so this is an exclusion when prints came from the same source, and this type of error can lead to guilty perpetrators going free. And this was found to be a little bit higher, around 7.5%. So 7.5% of exclusions were false negatives. And so, like I mentioned at the beginning, I'm primarily interested in individual differences when people are participating in surveys or participating in tests. And so here we can see the percent correct. So this is just 1 minus the overall error rate for each examiner. And so each circle on this graph is an examiner who participated in the study. This kind of tall stack of circles are all of the people who didn't make any errors in the entire study. And then everybody else made at least one false negative error. And you can see the people who made at least one false positive error in green kind of throughout the graph. And so this was kind of our first step, was to just look at the variation in percent correct across the examiners who participated in the study. But it's actually kind of hard to compare these percent correct scores because each participant saw a different subset of items. And so since not everybody answered every question, it's possible that some people saw a question pool that was harder than other people. And so it's not really fair to try to directly compare examiners in this way. And so the proposed solution that we outlined in the paper is called item response theory. And I think I have a quick overview, one slide from now. And so I think it's helpful to understand how I'm thinking about this data. And so usually in item response theory, we kind of think of these test responses as a matrix. And so each row of the matrix is an examiner response, and then each column is a different question. And so here we can see examiner 1 has a 0 for question 1, a 1 for question 2. They didn't see question 3, and so that's an NA, and then a 1 for the last question. And so here, zeros indicate an incorrect response or an error, and then ones indicate a correct response. And then the NAs mean that that examiner was not shown that question. And this is a useful way to kind of organize the data, because now we can think about wanting to understand the variability both across the examiners. So for each row, we want to have some measure of the variability, but we also want to understand the variability across each of the columns. So which questions are more difficult than others, and kind of why might that variability happen. And so now is the one slide intro to item response theory, which is probably the mathiest slide. And so item response theory comes from educational testing. So when students are sitting for different versions of the same exam, so things like the SAT or the ACT that are offered every year and multiple times a year. And so they don't reuse questions, but want student scores to kind of be on the same scale, regardless of which version of the exam that they see. And the idea behind the model is that we are going to model the probability of a correct response for each participant item pair. And that is going to be a function of participant proficiency, which we call theta, and item difficulty, which we call B. And so this is a really powerful statistical method because it allows us to account for participants answering different subsets of items. And since we're estimating effects for each participant and for each item, we can kind of isolate which factors are kind of going into each of the responses in that matrix. And so the model that we use is called a Roche model, which is for the statisticians in the room, just a mixed effects logistic regression with effects for each examiner, which are thetas, and then for each item, which are Bs. And then the Yij kind of maps back to that matrix on the previous slide, where I represents the rows and then J represents the columns. And so what we can estimate with this model is this item response curve. And so each of these curves that I'll show you will be for a different item. And so probability of correct response is shown on the y-axis, participant proficiency is shown on the x-axis, and we can kind of see that as proficiency increases, the probability that you get the question right also increases. And so this is kind of for an arbitrary difficulty of 0. And so if we have a easier item, that corresponds to a negative B parameter. And so now we can see that if someone has a lower proficiency, they have a higher probability of getting that question right, and that it increases closer to the left part of this graph. Similarly, if we have a more difficult item, that corresponds to a positive B parameter. And so now we can see that you need to have a higher proficiency estimate in order to kind of increase your probability of getting that question right. And so this is kind of the idea behind item response theory, and kind of the basis for everything that I'll talk about today. And so these are a lot of parameters to estimate. So we have a theta for each person, so 169 thetas, a B for each item, so 744 items. And so we're actually estimating a lot. And so I have chosen to estimate within a Bayesian framework. And so we model that matrix of ones and zeros according to a Bernoulli random variable, where each of the probabilities are that Roche model that I talked about. And then we put a normal distribution on both theta and B, and we estimate the means of the Bs and also the variances of the thetas. And so we're not restricting that kind of in any way. And so if we look at the false positive and false negative rates compared to that proficiency that we estimated, it correlates. And so this is a good thing because we want low error rates to correspond to high proficiency, and we want high error rates to correspond to low proficiency. And so I have the false positive rate on the x-axis on this left-hand graph. And so since there were so few false positive errors, it's kind of hard to pick up on any trends here. Since most of the examiners are kind of clustered around here at 0. It's a little bit more informative if we look at the false negative rate. And so here we can see that as you make more false negative errors, the estimated proficiency goes down. And so this is good. This is what we want. The other thing you might be wondering is why are these points colored in purple? And so those are the participants who made a false positive error. And so we can see that those generally also receive lower proficiency estimates, but this purple dot up here still received kind of a high proficiency estimate, even though they made that false positive error. And that's because this model doesn't distinguish between false positives and false negatives. And so that person, even though they made a false positive, made very few false negative errors. And so the other thing I want to mention is that what's nice about this data is that it also accounts for the difficulty of items that each participant answered. And so here is another version of that graph, but now the x-axis is just the observed score. So kind of taking both the false negatives and false positives into account. And I've colored the participants in purple here. And so these are participants that were between 0.94 and 0.96. So their observed scores are all really, really similar, basically indistinguishable from each other. And so we can look at their proficiency estimates, so those y-axis estimates according to the average difficulty of the question pool that they saw. And so that's what we have here. So now average question difficulty is on the x-axis. And so further to the left, so more negative average question difficulties means that examiner saw a question pool of easier items on average. And then the further to the right, those participants saw a question pool that was more difficult on average. And so we can see there's a slight positive upward trend. And so examiners who saw more difficult questions, but all got around the similar score, tend to get higher proficiencies. And so this is a good thing. This is kind of what we want item response theory to do. And also the model also implicitly accounts for the percent of conclusive responses. So the more data that we have for each participant, they tend to get a higher proficiency estimate. And I see a question in the chat about how was the question difficulty determined? And so the question difficulty is also entirely determined by the matrix of responses. So kind of going back to the Bayesian framework, all of the thetas and all of the B's, so the B's are those question difficulties, and everything is estimated by the model. And so this is knowing nothing about the items, nothing about the examiners, except for that response matrix. And so everything is estimated. And so the questions where there were more errors among everybody who saw that question got higher difficulties than questions that had fewer errors. But we have a problem here in that the black box data wasn't scored. So we know what a false positive is and we know what a false negative is, but the data actually has a lot of like no value and inconclusive decisions. There's still NAs in there. And so it's actually kind of a more complicated task than it might seem to map this into zeros and ones. And so I'll just walk you through what an example item looked like. And so the first task that each participant was asked to do for each item is a latent evaluation. So here they would see only the latent print for that item and report a value decision. So this could be has value or no value. I think in the actual study, they could report a value for individualization or a value for exclusion only, but I've combined them both into has value just because of some discrepancies in the data. If they responded that the latent print had no value for source decision, that question was done and then it moved to the next question. If they reported that it does have value for a source decision, then they would see the latent print or the reference print alongside the latent print and asked to make a source decision. And so this could be an individualization, an exclusion, or an inconclusive. And in addition to these responses, we also have reasons for decisions for the non-individualizations. So if the participant made an exclusion, they were asked to call it a pattern exclusion or a minutia exclusion. So a pattern exclusion means that there were kind of big details that, or the pattern of the prints didn't match. And minutia means that the participant had to look in the minutia of the print in order to make an exclusion. And then on the inconclusive sides, they could report a close inconclusive. And so there was corresponding information present, but not to the extent needed to make an individualization. No overlap, which means that there was no corresponding area between the latent and reference print for them to compare to, and then insufficient information, which was kind of a catch-all for just not enough information there. And so I have pooled the no overlap and the insufficient information responses kind of into one category, but treated the close inconclusives as kind of a different category, because it feels like maybe there's a little bit different information in that response than in the other types of inconclusives. And then finally, I won't talk about it today, but they also reported a difficulty of the question on a 5-point scale, so from obvious to very difficult. And I think in the paper, we have kind of an interesting analysis there of the variability and how the variability and how people are reporting that question difficulty correlates or doesn't correlate with their responses on the identification task. And so one thing that I'm really interested in as a statistician and a psychometrician is that there's a lot of variability in how often examiners report inconclusive and no value decisions. And so here we can see the distribution of inconclusive decisions that were reported for each examiner in the study. And so some people report very few and some people report as many as 50. And remember that this is roughly out of 100. So for some people, almost half of the questions that they saw, they reported as inconclusive, but most people kind of fall around 30. And similarly for the no value decision, so remember that this is just for the latent print only. Some people reported, again, around 50, so almost half of the questions that they saw, they said that the latent print had no value. And what's interesting about these responses is if they did report a no value, then the question was just done, and so there's no more information there. And so again, but we run into the same issue here that we ran into with comparing the percent correct, in that each of these examiners saw a different question pool of items, and so it's kind of hard to directly compare them. And that maybe the people who are on the right side of these graphs saw items that averaged to be much more difficult to analyze or much lower quality prints. And so one of the first things that I did when I started working on this project was say, okay, what are the different ways that we can score the inconclusives to kind of force it into this item response theory model? The first was to treat it as missing at random. And so this was how casework error rates were calculated. So they didn't count as errors or as correct responses. But as a statistician, I'm not crazy about this approach, since we do end up ignoring around 30% of the responses. And so I didn't want to completely get rid of all that data. We could also treat the inconclusives as incorrect. And so this penalizes examiners who are inconclusive very often, which maybe gives us a little better, a little more informative estimate of proficiency. But this is not great because it may actually be the correct response for low quality prints. And so maybe if an examiner sees a very low quality print, we actually want that response to be inconclusive. We could also take a partial credit approach. And so here we count an inconclusive or a no value as a partial credit. So it's not correct and it's not incorrect. And so this is a strong point of this approach is that it distinguishes between errors and inconclusive. So every inconclusive is not an error, but it still doesn't account for when the inconclusive is actually the correct response or when it's actually the incorrect response. And so again, I think this model was an improvement, but still not perfect. And then we also played around with different ad hoc scoring methods. So we used consensus answers, which was just if a person matched everybody else who saw that item, they were scored as correct, but if they disagreed, then it was scored as incorrect. We also played around with using the best answer. So if any examiner who saw that question arrived at the correct conclusion, so an individualization or exclusion, if anyone else reported an inconclusive, then that was marked as incorrect. And the list goes on and on and on. The more you think about it, the more scoring methods you can come up with. And that was really something that I didn't want to do, is I didn't want to kind of force my scoring method onto this data, especially when we don't actually have access to the original latent prints to have any sense of what answers should have been expected. And so if you've been kind of popping around rooms, you might have seen Heike's talk in this room earlier, which kind of looked at a similar issue and how inconclusive should be treated within these error rate frameworks. And so really what I wanted to do is, what if we don't do any scoring? So what if we don't call anything correct, we don't call anything incorrect, and we really just look at what the tendencies are to make these different conclusions? And so the approach is based really on 3 ideas. So first, it's important to better understand the variability of decisions among fingerprint examiners. It's unclear how inconclusive and no value decisions should be treated in the error rate framework. And so we wanted to kind of avoid forcing those decisions to be an error or a not error. And then finally, fingerprint comparison is a really complex task, and examiners are really doing a lot of different things when they're evaluating whether prints came from the same source or not. And so proficiency is by nature multidimensional, and so we really wanted to respect that multidimensionality of the proficiency. And so I think of this approach as having similar goals, but a different approach than in the recent Hicklin et al. Paper in Forensic Science International, which I have the full citation for at the end of these slides. And so the basic idea here, I know I'm getting short on time, so I'll go through this kind of quickly. So this is the IR trees framework of Dubak and Parchev. And so the idea is we basically fit a Roche model to each node in a decision tree. So the first decision is no value versus has value. The second decision is exclude or not exclude. Then I kind of think of the third decision as a match branch or a not match branch. If you go into the match branch, the 2 outcomes are either an individualization or a close inconclusive. And then if you go into the non-match branch, the 2 responses are exclude or inconclusive. And so if we want the probability of observing a close inconclusive for an examiner item pair, we just kind of go down the tree. So the probability that Y1 is 0, Y2 is 0, Y3 is 1, and Y4 is 0. I think I will skip this, and I'll just say that the tree that I present here was constructed using the process map from the OSAC Friction Ridge subcommittee. I'm not saying that this tree is perfect and that every examiner used that tree for every question, but it's kind of a useful way to organize the responses. And so for each participant, the model estimates 5 parameters: a no value tendency, a pattern exclusion tendency, a lean match tendency, an individualization tendency, and a minutia exclusion tendency. And so again, these examiner estimates are after accounting for the item effects. So we estimate all those same tendencies, but also for the items. And I saw this question in the chat earlier, asking about correlation between people reporting fewer no values, also reporting more inconclusives. And that is exactly what I will end with. And so if we look at these correlated tendencies between examiners, the highest one is between theta 4 and theta 5. And so this tells us that examiners who are likely to individualize are also likely to exclude. So people who are conclusive often are conclusive in both ways. And then the other thing I'll emphasize is that examiners who are likely to rate items as has value are more likely to use inconclusives further along in the tree. And so I think that is getting at MK's question, in that if people are using has value more often, it doesn't mean that they're magically finding information in these prints that other people couldn't find. It's that they're using inconclusives further along in the tree. And then the lack of correlation is also interesting. And so the examiner tendency to make pattern exclusions doesn't tell us much about the other decisions in the tree, because all of these correlations are close to 0. And we see a similar trend for items. So all of these roughly 0.8s in the middle are due to the conditional structure of the tree and just how many kind of matches and non-matches there were, and how they kind of flow through the responses. Oh, I went the wrong direction. And then the B4 and B5 in combination with B1 tell us the same thing that I was just talking about on the examiner side, but on the item side, in that items that are likely to be rated as no value also tend to be rated as inconclusive. And so I think I am out of time. And so I'll just end by saying, that I think IRT provides more information than a traditional percent correct scoring, especially in this case where we have really rich information. Modeling the decision-making process explicitly tells us where the variability is most likely to occur, and not just that there was variability across examiners. And I think IRT has a lot of potential in forensic science. So in other pattern matching disciplines where we know that there's probably variability in both the evidence that's seen, but also in the people who are doing the analyzing, in proficiency tests and other black box studies in other fields. And then I'll just end by saying that these results really underscore the importance of measuring and understanding the cognitive factors involved in latent print examination. This has been kind of a research need that's been identified in fingerprint analysis and also pattern evidence in general. And in order to understand something, you have to be able to measure it. And so I think that that is really the strength of IRT here. So I will thank you so much for your time. I know we are just over, and so if you need to take off, please feel free to do so. Otherwise, I'll stick around and answer a couple of questions for about 5 minutes.
Amanda, this is Karen. So Amanda Wilson raised a really good comment. I don't know if you can scroll back to it, but she asked, has CSAFE done any studies specific to criteria agencies use when reaching an inconclusive conclusion? And relatedly, I sort of was wondering about that myself, because in your suggested treatments of inconclusives, the first one was treated as missing at random, but we don't really believe that, right? That somebody reported inconclusive just because they flipped a coin. So I think she's raising a really good point, which is, is there additional information that we could solicit from the examiners about why they chose inconclusive? And it seems like your model is flexible enough that perhaps it could incorporate that. I'm not, somebody who works in the forensics lab, so I have no idea how difficult or how non-responsive forensic practitioners might be to adding to their workload by asking them to be a little more specific about why.
Yeah, I think that would be very interesting. And I think, so in this data that we have, there was those reasons for inconclusives. And so the close inconclusive as opposed to the other types of inconclusive, I think that does have some information in it. And so I think that it would be really interesting to dive into when agencies kind of allow inconclusives and what their kind of practice is. Another thing I'll mention is in the proficiency tests, this is another thing. I don't think that inconclusives are really reported in proficiency tests. And so I think that is another place where, we could collect more data. We could see what is it that is leading to an inconclusive, and why are some folks more likely to use inconclusives than others.
So proficiency tests that's not an option, or it is an option, it's just not reported? So
it likely varies based on the proficiency testing agency, but so for instance, I'm most familiar with the CTS proficiency tests. And so those, you can report which finger of which person the print matches to, or not identified. And so it's unclear whether not identified is not identified because there wasn't enough information, or not identified because the person wasn't there.
Okay, reinforcing again what Amanda Wilson is suggesting. Thank you.
Yeah, exactly.
Amanda, has there been any movement in the fingerprint area? I'm a forensic document examiner, so we have qualified opinions. So you can say probably, which means more likely than not. Strong probability means virtually certain, but you don't have to go to the extreme of identify or eliminate. So has there been any movement in the fingerprint arena to have qualified opinions rather than unqualified?
Yeah, I think there has been some. I know Simon Cole is actually in breakout room A presenting on probabilistic reporting, which isn't exactly what you're talking about, but I think it's related in that, like, not all exclusions are created equal kind of thing. Some are extremely clear and others are more borderline. I think that in this 2020 Hicklin paper that I have up on the screen right now, they talked a little bit about examiners having different thresholds in their inconclusive and exclusion decisions. And so I think that is also kind of related. I'm not sure exactly what the status of the field is in terms of these qualified conclusions, but I think that it seems as if there's maybe a little bit more movement in that direction.
Thank you.
And so Amanda Wilson has another wonderful question in the chat. about the suggested sample size for the Roche model. And really let's see if I can find it. So I didn't talk too much about what these uncertainty estimates look like, but here are some of the uncertainty estimates for those different theta estimates. And so the trade-off here is that the bigger your sample size is, the smaller these error bars get. And so you can, I think that you can fit a Roche model with 50 to 100 participants and some number of questions, but the trade-off is kind of how wide are you willing your error bars to be. I guess I'll say that I think the main constraint to implementing this in practice is that you really need to have multiple responses per item. So we could take a look at casework and try to get some data there, but when only one examiner sees each item or each potential case, then we can't really separate out what's due to the examiner and what's due to the item. And so you really need to have a substantial amount of examiners see each item, which I would be happy to chat more about. And so I think.
Hold on, I have a question, Amanda. Sorry to jump in. Do we have, we've been looking at the issue of inconclusives in firearms examination, of course, but do you have any idea in latent print examination what proportion of real cases end up in inconclusives?
So I don't know, except I did watch Brett Gardner's presentation just now. And so they looked at the blind test cases in the Houston Forensic Science Center. And I want to say it was around 30 to 50% were inconclusive. Maybe someone is more familiar in here who can correct me if I'm wrong, but I believe it was pretty high.
So, I mean, in the ballpark of what happens in black box testing?
Yes.
Okay, that's interesting because, the proportion of inconclusives in firearms black boxes is about 30%. But there's absolutely no information on what the real case inconclusive proportion is for firearms examiners. Interesting.
Yeah, and I think that it's another thing that's very hard to measure because I think different agencies have different reporting standards in that like latent evaluation. So just kind of looking at the initial evidence and sort of whether to run it through an APHIS system or proceed with a further analysis. I'm not sure how standardized the reporting is for those types of decisions. Yeah, I think this issue of what is an inconclusive? Is it an inconclusive because of the latent? Is it an inconclusive because of the exemplar? Is it an inconclusive because there's no corresponding area between the prints? I think these are all really, really interesting kind of complications to the data that I would love to have more data on.